Hello everybody, today I'm going to do a walkthrough video of the British Informatics Olympiad 2023 round 1 questions. Fortunately I was lucky enough to be invited to the second round and I decided to make this video to hopefully help people in the future with bio round 1 questions. This year to get into the finals you needed a mark of 85. And I was right on that boundary and managed to just scrape getting in. But I'm sure my advice will be useful to you, so make sure you listen attentively. And if you have any questions, leave them in the comments, I'd be happy to answer. But let's just get straight into it. Actually, one more thing. If you want to see the round 2 answers, I recommend checking out my friend Erekle's channel, which I will leave in the description. He's a lot better at this stuff than I am. And he's got the answers to the round 2 questions coming up soon, probably within a couple of months, so look out for that. And I think he already has some solutions for 2019 questions, I think, but I'll double check and I'll leave his channel in the description so you can have a look at that. But without further ado, let's get into this year's bio questions. So first we have the Zeckendorf numbers, so let's look at what this question says. So this question was quite easy. Question number 1 is usually the more accessible one. And it's based off the Fibonacci numbers. The key point you have to take away from this description is that the Zeckendorf representation for n always includes the largest number from the Fibonacci sequence that is no greater than n. So this question is quite simple. All we need to do is we get the greatest Fibonacci number that's less than or equal to a number. We output it and then we subtract that number from our current number, and eventually it will just print out all the numbers in the representation, and we just keep repeating this until n is 0. And the way we calculate Fibonacci numbers is quite the most common method is using a table. So you can imagine in our table, let's just imagine the table of Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, so on. So what we do is our A and B are first set to the first 2 numbers 1 and 1. And on each iteration on this loop, we want to shift our window of A and B to the right by 1. So A, the new value of A is what B used to be, and the new value of B is equal to A plus B, because that's how the Fibonacci sequence works. So if you imagine we shift our A and B values along, so now A turns into what B used to be, and B turns into what A plus B used to be. So you see how this works? So we use this principle to continually generate Fibonacci numbers until we are up to the limit, and once B is greater than our limit, we know that A must be the biggest number that is less than or equal to our limit, so we can return A. So pretty simple. And we just do that, and that should be it. We can test our program with some of the inputs from the mark scheme. Let's just test it with this one because it looks the most complicated. And let's take this output, put it here, and check it against the output that's on the website. And it's the same thing, so our program's working, which is good. It would be embarrassing if it didn't, and I would definitely cut that out and record it. So yeah, anyway, that's the easy part. Now we're going to get on to the more tricky questions, which are these 2 markers and 4 markers. Luckily on this paper there were no proof questions, which I always suck at. These ones were just kind of making auxiliary programs to calculate answers to questions. So on part B, what is the highest number under a million whose Zeckendorf representation consists of a single number? Okay, so now you have to think, if the Zeckendorf representation only has one number, that must mean that when you take that number away, you have 0. That means that the number itself is a Zeckendorf representation. Sorry, is a Fibonacci number. So basically all this question is asking is, what is the highest number under a million, which is a Fibonacci number? So that's very simple to do. All we do is use this function that we made before and just put 1 million into it. And if we run it, it's going to calculate it very, very quickly. We get 832,000. And if we check the mark scheme, there it is, 832,040. That's the answer we got. Okay, pretty simple. I'm going to blast through question 1 because it's not too difficult, and the other questions will take a bit more time. Right. 1C, how many numbers under 53 billion have a representation consisting of 3 numbers? So you might think, okay, let's just iterate through all 53 billion numbers, but that's not possible. It takes a computer about, what, 1 or 2 seconds to do like a couple million iterations. So to do a couple billion, that might take a whole hour. I mean, maybe you have time to do that in the test, I guess. You just start running the program at the beginning, and then at the end of the 2.5 hours, maybe you have an answer, but I doubt it. Especially if you're using an online IDE. Anyway, you definitely wouldn't want to do that. What we can do instead is we make the key observation that if a Zeckendorf representation, if a number can be represented as some, okay, let's suppose that the representation of a number contains 2 adjacent Fibonacci numbers. If it can contain 2 adjacent Fibonacci numbers, then it might as well just contain the next Fibonacci number above them. So we will never have 2 Fibonacci numbers A and B that are consecutive in the representation. So we can actually just count how many ways there are of choosing 3 adjacent Fibonacci numbers and just make sure that the sum is below 53 billion. So what we can do is we can generate all the Fibonacci numbers up to this limit, which is a bit odd. I don't know why it's so specific. It's probably a Fibonacci number itself. Anyway, it doesn't matter. And we just count how many Fibonacci numbers there are below that limit. And then we iterate through and we count how many different ways there are of choosing 3 of these Fibonacci numbers to make a representation. But we make sure that we don't pick 2 adjacent ones, because if we pick A and B, then they're adjacent, well, the representation won't actually contain A and B, it will just contain A plus B. So we just have to make sure that we're choosing numbers that are not adjacent to each other, and we can do that by just adding 2 onto I instead of adding 1. And there's probably some formula to do this, but I don't know it, so you can just make a for loop. And if we run this program, it will give us 18,424, which is the correct answer. So the key insight you have to make there is that instead of checking every single number, you can actually generate the numbers and just count how many there are. So that's one common method of solving problems. You kind of don't think, okay, how many numbers in this range will satisfy this condition? You think, okay, can I generate numbers in this range that satisfy this condition? And how many of those can I generate in this range? And that usually is a lot faster to answer. Okay, now we're going to go on to 1D, which is a bit more challenging. So I'm sure there's an easier way to do this, but my method, I think, works pretty well. So the question asks, how many numbers between 1 billion and 5 billion do not have that in their Zeckendorf representation? Again, 4 billion numbers is quite a lot to iterate through, so you probably won't be able to do that in time. So what we're going to do is we're just going to make a program, and we're going to figure out a way of counting how many numbers in this range have that in their representation. And we're going to generate these again. We're going to construct this solution instead of checking everything in the range. So when I was solving this in the test, I thought it's probably easier to figure out how many numbers do have it in their representation, and then we can just subtract the total numbers in the range. We can then take the number of numbers that do have it in their representation away from the total range to get the number of numbers that don't have it, which turns out to be not too difficult. So I'll just walk you through this code. Actually, first I'll explain the key insight, is that if we can reach a number that contains this in the Zeckendorf representation, then that number will also contain it, obviously, because the representation of a Zeckendorf number is made up from the largest Fibonacci number that is below it, plus the Zeckendorf representation of the number when you subtract it. So it's like if this number will have 700 million, then think, okay, to get to this number, how can I get to this number? Well, I can get to this number by subtracting another Fibonacci number higher. So I just consider, so first we note that any number, that all the numbers between the limit, I call it limit, all the numbers between the Fibonacci number that they give you and the one above it, they will have that number in the representation, because this will be the largest Fibonacci number less than n. So what we do is we use the same code that we had before to calculate A, which will be this Fibonacci number, and B, which will be the one above it. And then, so what we can do is we can create a list of ranges, and we say between this number and this number, all of these numbers, they have this Fibonacci number in their representation. So we can begin our first range by just taking the Fibonacci number and the next one above it minus 1. All the numbers in this range will have this in their representation. Then we go through all the Fibonacci numbers up to 5 billion, and we say, well, if we take this range and we add on this Fibonacci number, then that gives us a new range which also has that number in its representation. So we can add that to the list of ranges, and all we do is we make sure that the lower bound of the range is less than our Fibonacci number, because we need to make sure that the Fibonacci number we're choosing is higher than the numbers we have right now. Because if, let's say, we have a range that starts from 2 billion, and then we say, oh well, if we have 2 billion and then we add a billion onto it, then we subtract 1 billion and we get there. But remember that the question says it always picks the largest Fibonacci number. So if the values in our range are less than, are more than the Fibonacci number that we're trying to remove, then that's not the actual number that's going to be removed, it's going to be something different. So we just have to make sure that we're checking this before we add the new range into our list. But once we have our list of ranges, we can then just go through them and make sure that the range isn't some weird out of bounds, because this isn't, this will generate some ranges that are like from 6 to 8 billion or something. We can just remove them, ignore them. And then we get the beginning of the range and the end of the range. So what I've done here is I've said we get the maximum of the start of the range and the 1 billion. So if the range starts at 780 million, but our lower bound is 1 billion, then it will just take that lower bound. But if our lower bound is 1 billion and the start of our range is 2 billion, then it will accept the 2 billion as the actual beginning. So we're just clamping the range into our 1 billion to 5 billion domain. And similarly for end, we can do the same thing, but we clamp it the other way. We make sure that the end of the range is never above 5 billion. And then we can calculate the range by just doing one end minus the other end plus 1. So if you imagine, for example, if we have the range of numbers from 3 to 5, that's 3, 4, and 5. So we need to take the difference between 5 and 3 and then add 1. So similarly, we just do end minus begin plus 1, that gets the size of our range. And we have our answer, which is going to be just the sum of all the ranges. Then we can get the size of the big range. And this is 5 billion minus 1 billion, again plus 1. Because the question says inclusive. This is very important, inclusive. So all the numbers between 1 billion and 5 billion, but we also have to add the one for 5 billion itself. So make sure that this is actually if you don't add 1, if you're off by 1, you just get 0 marks. They don't even allow you that. So you have to be very careful. And then once you do that, we can just get the big range minus all the small ranges inside of it, and that's our answer. So if you run this program, we get, so here I've printed out all our ranges. So you see we have this one, this is very annoying, what's going on? So we have this one, which is the one I was talking about. Obviously all numbers in that range will have this Fibonacci number in their Zeckendorf representation, and then we're just adding on the next biggest Fibonacci numbers and creating these ranges, and then subtracting the we're subtracting the inner ranges from the outer ranges, and we're ignoring these ones that are like out of bounds because they don't matter. And then we get this as our answer, and if we look at the answer booklet, this is the correct answer. This was one of the questions I missed because I tried some like other method, but it wasn't actually correct. But this is a method I thought of the other day when I was revisiting the problems. So that's the end of question 1. Take a break, relax, drink some water, eat some food, come back for question 2. Question 2 I think is the toughest one, so get ready and we'll get back into it. Okay, welcome back. Hopefully you rested up, and we're going to get into question 2 now. When I saw question 2 in the test, I thought, oh no, this is very hard. But then I thought about it for 20 minutes, and then I actually realized, oh, it's not actually that bad. Some of these questions here are quite tricky. 2A is not too bad. Once you make the foundation for 2A, the other parts kind of follow along, but making the what I did as a class to allow for all this functionality is the hard bit. So what we're going to do is, the question says, calculate how many ways a pair of pentominoes can be combined. So what we have is we have all these shapes, each one corresponding with a letter, and we think, okay, if we take these shapes and we try and join them together in every single way possible such that at least 2 edges are connected to each other, how many different unique shapes are there that can be made? So there's 2 bits to that. The first bit is we have to try and connect the shapes in every way possible. The second bit is checking how to check whether 2 shapes are unique or if they're the same thing. So let's think about the first bit first. How are we going to find a way to combine the 2 pentominoes in all ways possible? Well, what you can do is you can take this pentomino, let's say we're checking F and G. You can take F and keep F fixed in place. Then you take G and you then move G. You imagine a grid around F, and it extends, let's say, 10 squares in all directions, just for simplicity's sake. We can then take G and put G centered on every single square in that grid. Then we can check that A, none of the boxes overlap, because we can't have 2 squares of the shapes overlapping. And B, we need to check that at least one of the sides is connected between F and G. So when you think about it like that, it makes it a lot easier to code. So let's go into our pentominoes library. So I've let's start with the annoying bit, which you might see in this preview, which is down here. So the annoying bit is that you have to enter, you have to enter in the shapes of all the pentominoes into a program. So the way I've done it is that I've looked at all these shapes and I say, okay, the maximum width of a shape is 3 squares. You can't find all these shapes are maximum 3 squares wide. And the maximum height of one of these is I, which is 1, 2, 3, 4, 5 high. So what I've done is I've represented each pentomino as a piece of data, as a vector or array list or whatever, as an array that's 15 long. And so you're basically just giving the squares an order. So you'll do top left, top middle, top right, bottom left, bottom middle, bottom right, and so on all the way down. And so you're just giving it row by row, left to right. So for example, for F, we would represent it as 0, 1, 1 for that top row. Then 1, 1, 0 for that middle row. So you 1, 1. So you have this square, not this square, and not this square. Then 0, 1, 0 for this bottom one. And then we can just fill in the rest with zeros because it's finished. And then we enter in all the letters like this. I think it took me about 10 minutes to do that. Maximum 10 minutes. I think it took me about 5. But you can do that pretty quickly. It doesn't actually take too long. But once you have this, you can now convert this into what I'm going to call a point set. So I have this class called point set. And what this point set class has is it has a bunch of points represented by Cartesian coordinates, x and y. And so for example, oh, wrong thing. For example, F, this would be, let's say the boxes would be one, what would it be? Let's look at our program and find out, shall we? So we're going through row by row, column by column, and we're getting the index. So this F would look like, it would have a block at x equals 1, y equals 0, x equals 2, y equals 0. It would have a block at x equals 0, y equals 1, x equals 1, y equals 1, and it would have a block at x equals 1, y equals 2. And so our point set class is just basically, as the name suggests, holding this list of Cartesian coordinates, and we then provide a bunch of helper functions, which I'll go through in more detail in a minute, to provide the functionality for our programs. And you actually see that the code for our programs is very short. This library is the main chunky bit of a program. It's about almost 250 lines. I think when I wrote it originally, it was a lot shorter, but I've just written it a bit more verbosely, just to make it easier to understand. But if you're confident with your programming, you can probably write this whole thing in like 100 lines. Well, I don't know, this bit takes about 20 by itself. But yeah. Okay, anyway. So now let's, I'll just explain this function real quickly. So we're basically just going through all the y's from 0 to 4 and all the x's from 0 to 3. Again, because I said it was a 3 wide and 5 tall grid that represents each pentomino. The index is just y times 3 plus x. You can verify this is true. For each row you go across, you're skipping 3 boxes. And your index on the row you're currently on is added on. And if you have a 1 in that position, then we can add x and y into our point set. Okay, so now we can convert from a pentomino into a point set. That's basically all that this class does. It just allows us to load a letter into the data and then convert it into 7 points. Pretty simple. And we just have a function here called fromLetter that will take in letter, create pentomino, load it into the pentomino, and return the point set. Okay. Now we're onto the juicy bit of the program, which is the point set class. Well, one thing, if you're coding C++ and you don't know the difference between a class and struct, they're exactly the same thing. A class by default has all its variables and functions privated. A struct by default has all its variables and functions in public. So I've just written struct. I could equivalently write class here and then write public colon and then everything has to be public. But struct works, and yeah, why not? Okay, so first, these methods are pretty simple. I can add either one point at a time, which is a pair, and it just adds it into this vector, or I can take in a vector of points and add them all into here. Pretty simple, that's just adding points into our point set. Next, we're going to have a bounds function, and what this does is it gets the minimum x and maximum x of our set of points, and the minimum y and maximum y, and it returns all four in a tuple. There's min x, min y, max x, max y, and you'll see that a lot of these later functions will use the boundaries. Next, we have size, and so what this does is instead of returning min x, min y, max x, max y, we're just going to return width and then height. So that's pretty easy to calculate just by using the bounds we have and then just doing the same thing we did similar to 1D. I'll skip normalize for now and I'll come back to it. So equivalent, this is checking whether one point set is equivalent or represents the same shape as another point set. So this one's pretty simple. First we check that they contain the same number of points. Pardon me. And then we go through all the points on our point list and we check whether the other point list contains that point. If it doesn't contain that point, we can return false. If it does, we can return true. If it contains all the points, if both point sets contain the exact same points, we can then return true. And in fact, I think we can simplify this code, which I'll do really quickly. We can actually just check other dot why is it not dot contains point, and if it doesn't contain, my VS Code is very bad. Okay, it doesn't let me do that because this is a const, and I'll explain why I've done that later. It doesn't let me do that because this is marked as const and this is not marked as const, and I could mark this as const, but I can't be bothered, and this works fine, so I'm not going to break my program. But yeah, that's pretty simple. Now touch, this is again, as I was saying before, how we have to check every single arrangement of the, we keep on fixed in place and we move the pentominoes across all the possible spacings. We have to check A, that they don't overlap, and B, that they touch. So to check that they touch, we just go through all the points and check whether the distance between any 2 points is 1. If the distance between any two of the points is 1 square, then they must be touching. So if any 2 points are touching, we can return true, and if none of the 2 points are touching, we can return false. Then overlap is very simple. We just check whether the other point set contains any of the points in the current one. If it does, then they're overlapping. If it doesn't, then they're not. Contains, this is just going through all the points in our point set and checking whether we match the desired one. Shift, which is related to normalize, I will come back to it in a minute. These three functions are all for part D. Now I'm going to explain, actually, last one. So I'll do print first. So print here, we're getting the boundaries of our shape. We're going through all the possible squares, and we're printing a hashtag if there's a square, and dot if there's not. This is just while you're debugging, it's a helper function you can use. Lastly, I've done this thing in C++, which I'll come back to this later, but it just lets me check whether 2 point sets are equivalent by using the equals equals operator. So instead of doing like point set 1 dot equivalent point set 2, I can just do point set 1 equals equals point set 2. But this is actually necessary for a later bit of a program. Now let's talk about the overlay function. So what this function does is, given 2 point sets, it will return the all the different shapes that can be generated from connecting them. First, we normalize the points that we're overlapping. So what I mean by normalize, now I'm going to explain. When we're checking whether two point sets are equivalent or not, one issue is that, let's take this eye example. This eye shape is represented by a point at, is represented by a point at x equals 1, y equals 0, x equals 1, y equals 2, x equals 1, y equals 2, x equals 1, y equals 3, and x equals 1, y equals 4. Now imagine we had another eye shape, but let's say it's shifted to the right by 5 squares. So that other eye shape is at x equals 6, y equals 0, x equals 6, y equals 1, x equals 6, y equals 2, so on, so on, so on. If we just compare the 2 point sets at face value, we're not going to think that these point sets are equivalent, but they actually do represent the same shape. So what we need to do is we need to normalize them. So what I mean by normalize is that we shift the top left square of our shape into the origin. So for example, right now this eye shape is at this top middle square of the eye shape is at x equals 1, y equals 0. What I want to do is I want to shift all the squares at once so that the entire shape has its origin at the top left. So now instead of x equals 1, y equals 0, it's going to be x equals 0, y equals 0, that's x equals 0, y equals 1, 2, 3, 4. And the other shape that we had, which was 6 squares, that was at x equals 6. We then shift that 6 to the left so that its center is always, its top left is also at 0, 0. And now when we compare the 2 point sets, the points will all be in the exact same place. So this is the key to how we're checking whether 2 shapes are equivalent or not. So now if we go back here and we look at our normalized function, all we do is we get the bounds and we shift our shape minus the minimum x and minus the minimum y. So for example, in F, this empty square here will be centered at 0, 0. And so if we have two shapes if we have two sets of points that have the same shape, but they're not in the correct position yet, they will be shifted to the same position that is the same for both shapes. And that is just the minimum x and minimum y, i.e. the top left, even if it's empty. So if let's say this shape F, if this top left empty box is at x equals 3, y equals 2, we shift the shape minus 3 along the x-axis and minus 2 along the y-axis so that it is now at 0, 0. So pretty simple. And the way our shift function works is that we go through all our points and we just add on the dx and dy. Very simple. So now let's go to the hardest function in my opinion, the overlay function. Actually, I think the wholly function is a bit more challenging. The overlay function. So we're going to first create an empty vector, which is our answer, which is just a collection of shapes that can be made from arranging 2 pentominoes. Then we're going to normalize the 2 shapes that we're arranging. This is just so that this calculation here works. So what we're going to do is we're going to get the sizes of the 2 shapes, the widths and heights, and we then want to figure out how we maneuver the 2 shapes around. So one shape is locked at 0, 0, right? So the furthest along to the left we should go, realistically, is going to be the negative of the size of the other shape. So for example, if I'm keeping I fixed in place and I'm trying to rearrange F around it, so I have I fixed at 0, 0 in the top left. The furthest to the left I'm going to shift F is going to be 3 because its width is 3. So I'm only ever going to be having F 3 to the left of Y, and so that its shape is always going to be touching. And we're going to increase the dx up until the size of this one. So we're gonna make the top left of the shape that we're moving equal in the highest case to the square directly to the right of our shape I. Because the width of I is 1, the furthest along to the right we're going to move our shape will be exactly next to it, which should make sense. Pardon me, I have a lingering cough, so my voice is a bit bad as well, so apologies if I'm coughing or I stop talking for a couple of seconds at any point. Anyway, then we use the same principle for the change in y and change in y, sorry. So again, we go up to maximum the negative height, and we go down to maximum the height of our fixed object. Okay, so now we have our grid that we're going to place around our fixed pentomino. Now we're going to create a new point set. We're going to add all the points from our fixed pentomino. Sorry, from the pentomino that we're maneuvering around, and we're then going to shift that into the correct position that we've defined by our dx and dy coordinates. Then we're going to check that the current pentomino that's fixed in place is not touching this maneuvered copy, and sorry, is touching and is not overlapping. So again, the two conditions I talked about earlier. If they satisfy these conditions, then this is a valid arrangement of the pentominoes in space. We can then add to our maneuvered shape the points of our fixed shape, which now will represent the conglomerate of the combined pentomino. And now we normalize that shape. So whenever we get that shape, we then normalize it so that its top left is at the origin. And that's just so that we can now check of our point set vector and check that we don't already have this shape. And it doesn't matter if we make two shapes from different arrangements, because we normalize them, they're going to flag up as the same shape as long as they do have the same shape. Their position doesn't matter because we shift all of their positions to the top left origin. If we don't already have this point set in our answer, we can add it to our answer. At the end of this loop, we return our answer and we have our vector of shapes. And so now for C++ users, so you don't have to worry about this if you don't do C++, but to use this find function that does a linear search, you have to have implemented this equality operator. This is how it does a linear search. It will use this equality operator to check whether it's found your item. So I create this equality operator and I use it, and the find function will use it. That's why I use it. That's why but I'm getting my words mixed up. That's why I define it. Okay, so now we can overlay one current point set with another point set. What if we want to overlay our current point set with a we want to try overlay a bunch of different points. We want to overlay our current point with A, and then we want to add another shape, and then a different shape, and we then create a vector of all the different ways of arranging those. Well, that's just pretty simple. We just go through all the shapes that we want to arrange with. We use our overlay function to get those shapes. Those are conglomerate shapes. And we use the same logic as before. If we don't have it, push it, and we return ABC. So now we can overlay a point with a bunch of other different points, which we'll use in part C. And I'll come on to the holy function, holy, later. Part A, once we've made this library, which should take you, I think it probably took me about 45 minutes in the test to make that, which is reasonable. Once you make that library, now you can, now it's really easy to make part A. Okay, let's take one of the inputs from the mark scheme. We'll take QP, we'll do FF, QP, and VI. So let's do FF first. Cool thing is, if you just write if input equals FF return 1, return 7, you'll just get 1 mark. So let's type FF in, get 7. Now let's test it with QP, we should get 14. I hate my VS Code, sometimes it just doesn't let me write stuff. And now it's going to throw an error because I have QP typed. Amazing. Apologies. I think I just have to give it a bit of time to cool down. Okay, QP 14, perfect. And now let's test it with VI. VI 19, perfect. So it works. Definitely passed. Don't know what's happened there. I don't care. Whatever. I don't know what's going on. Anyway, my computer's a bit buggy sometimes. Okay, so that's part A. Part B. Let's see what this question says. I'm going to remind myself. How many shapes made from combining X and W can also be made from 2 other Pentominoes? Okay, now that we have our library structs, this is pretty simple. We can just, first we get the set of shapes made by combining X and W. Then we go through all the other different Pentomino pairs and we check every time we make a shape that comes from this set, we can add one to a counter and then remove it. So I've got the point set XW, which I've just made by overlaying X and W. These are all the letters that we have in our Pentominoes, and then we just go through all the different ways of choosing them, make sure that we're not choosing X and W again. We make our 2 point sets, overlay them, and we go through all the point sets. If we find the shape made from our 2 letters in the set of shapes made by X and W, we can increase our answer by 1 and then erase that from the vector. Now if we run our program, we should get the correct answer, which is 1. If I got that in a test, I would be very scared. I think I did get that. But yeah. Oh yeah, I did get this. I actually got 2C wrong. I lost 3 marks here, but I'll explain why. Right, 2C. This one is it's not too difficult. There's just one thing you have to spot. So the question is, how many distinguishable shapes can be made by combining III and LIV? So to combine III, we can just take I, overlay it with itself, and then overlay I with all the different shapes made from overlaying I with itself, and we can just print out the size of that. Pretty simple. Now the tricky bit is when we're working with the LIV, because it's actually a bit misleading. You think LIV is arranging the Pentominoes I and V and then L. Maybe you think that. Maybe it's just me. But it actually includes arranging I and V and then L, or arranging L and V and then I. So you actually need to think about both ways. So you can combine I and V by, you can overlay I and V and then overlay L with that. Or you can overlay L with V and then overlay I with that. And so you have now we have 2 different point sets. And then we use the same logic as before, checking whether the shape is not already in LIV, and if it isn't, then we add it. And then we can print out the size of LIV. So if we run this, we should get 122 and something else. 122, 67. There we go. 5 marks. Lastly, part D, which is a bit challenging. So I got this wrong in the test because I think I got the answer 79, but I kind of misinterpreted what it meant by being holy. Well, I didn't misinterpret it, but I didn't think about the type of holes that we could get. So it tells us, so okay, I haven't actually read the question yet. How many pairs of potentially identical pentominoes can be combined to form a shape with an internal hole? So if we look at what it means by an internal hole, it says that note the last combination contains an internal hole. There is a gap inside the combined shape. And you see this gap here. So you would think To check whether there is an internal hole, all we need to do is find a square that is empty. For each square in our shape, we check, is that square empty, and is the 4 boxes around it not empty? But that's not actually correct, because I forgot exactly which shapes you have to combine. Ah, here we go. Okay, let's say you have V and G, and let's say you put G there. So you put G, you put this square of G there. When you connect them, you actually have an internal hole of 2 squares. So we actually need to check that our internal hole is too big, is either 1 or too big. So what I've done is I've actually made a function that checks whether it's any size big. So if I can find it, it's in lib, obviously. So our holy function here is going to go through our all our boundaries. So it's going to go through all the squares, and it's going to check if we contain a box, then there's not going to be a hole there, so we can just continue. If otherwise, we can then check. We can use hold that function to check whether there is a hole at the specific coordinate, or originating from the specific coordinate. Let's look at this hold that function. So what we do is we first check, is x and y outside of the shape. If we're trying to look for a hole and it's not even in the shape, and it's like here, like it's not even in the shape, obviously we can return false. That's not an internal hole. Otherwise, we then go through all the coordinates that are adjacent. So x minus 1, y 1 to the left, x plus 1, y is 1 to the right, x, y minus 1 is 1 up, x, y plus 1 is 1 down. We go through all those points and we check for all of those points if we contain next. If we contain next, then that's good. It's a wall, and we can just move on to the next square. If we don't contain it, it could be that it leads to the outside. It could also be that it's an internal hole that's bigger than just the one square. So what we can do is we can add to our points the the square xy, and what we do is when let's say we're checking, let's take this VG shape. Let's say we're checking for the hole here. We check the top, okay, it's a wall, good. Left, it's a wall, good. Right, it's a wall, good. Down, it's not a wall. So what we're going to do is we're going to fill in the square that we came from, and then check whether the one below from it is now an internal hole. So what we do is we fill in the square that we came from, and we then use the same function again to check whether that square that we're looking at is its hole itself. Because if that function is a hole when this one's blocked, that means that we actually have a hole of size n plus 1. And after we call this function, we have to remember to remove that blocks that we added, so that we don't mess up the later functions. And if it turns out that that if for any of the sides it leads to the outside, we return false, because it's not a hole. If any direction that we can go in leads to the outside, it's false. And that's how the whole function works. So if we run this program, we should be able to get 84. There we go, 84. Perfect. That was a tricky one. I got that wrong. I will admit that. But that's question 2 done. That's the hardest one. Question 3, I think, is definitely harder than question 1, but I think it's simpler than question 2. So take your well-deserved break, get a drink, get a snack, and come back ready for question 3. I'll drink my cream soda. Okay, welcome back. We're on to question 3 now, and this one is not too bad. So, like question 2, there's kind of like a bulky program that you have to do for part A. Well, it's not that bulky. It's actually only about 50 lines of helper functions, which isn't too bad. But once you have these, the other questions are pretty easy, except D. D is a bit tricky. But let's go through it. So first, let's explain the principle of what's happening. So we have 4 pegs, and we have a ball on each peg represented by a number. 1, 2, 3, and 4. And we can move the balls between the pegs by just taking one off the top of one peg and moving it to the top of another peg. Might remind you of Towers of Hanoi, but there's no constraint on which balls can be added to which pegs. So not until part D anyway. So, I mean, you can read this question and make sure you understand it. But I assume you do if you've done the test already. So I'm just going to explain what our program is going to do. So what we can do is we can model this as a graph, and each state of the pegs represents a node in the graph. Each edge in the graph represents a move you can do, moving one peg from one point to the other. We can construct our graph, and once we have our graph, since we're finding a minimum number of moves, we can just do a breadth first search. In other words, what we're doing is we're saying, and this is in a non-graph theory explanation, we think we get how many we get all this list of states that we can reach in 0 moves from our starting position. And obviously that will just contain the starting position and nothing more. Then we also get the list of states that we can reach after 2 moves. And sorry, 1 move. And that's just all the states you can get if you start at the starting state and you think of all the different ways of moving one ball from one peg to another. That will be the list of states you can get to in 1 move. Then, to get the list of states you can get to in 2 moves, you just take all the states we have right now, and you just, for each of those, you then think, oh, like how many, what are all the different ways of moving the balls across pegs for each of these states that we have right now. And we can then generate all the states we can get to in 2 moves, and then 3 moves, and then 4 moves. And as soon as we get to a state, we know that this must be the minimum number of moves to get there. Because we tried every single possibility, and it's the first time we got there, and it's after n moves, n must be the minimum. So that's how our BFS, or you don't have to call it a BFS if you don't want to, but it's just a breadth first search. We're checking all the states at distance 1, all the states at distance 2, all the states at distance 3, all the states at distance 4, and so on, until we finally find our state. So what we're going to do is we're going to have we're going to represent each state not as a vector, because we can't easily have a vector in a map or a queue. What we're going to do is we're going to represent each state as a string, and we're just going to take inspiration from the question, and we're just going to get our pegs, and we're just going to represent our state as just a string separated by spaces of which balls on each peg. So to do that, we create an empty string, go through the pegs, and we add on the value of this peg into our state. And if it's not the last peg, we can just add a space. So peg, space, peg, space, peg, space, peg. Or there's only 4 pegs, so it'll be peg, space, peg, space, peg, space, peg. Then this is called a hash, by the way. When you're representing a state in a graph or any system, not by a complex data structure, but just by something like a string or an integer, which can be used in a map or a set or a vector. Well, I mean, yeah, pretty easily. Map or a set. Now we're going to unhash, so now we have to figure out, okay, we can convert 2 hashes, what about converting from hashes? In C++, it's a bit annoying because you don't have a string.split function, which will split a string into parts based on a delimiter. So I've had to code that myself, and it's not too difficult. What we do is we have a start position, which is just the start of the peg, of the current peg. We look for the next space. If we can't find a space, that means we're on the last peg, and we can just add the rest of the hash into our pegs. But if we do find a space, then we take the substring of that peg from our start to right before the space. We add that onto our pegs, and then we set the start point of the next peg to the position of the space +1, which should make sense. And once we're done with that, we can just return the list of pegs. Now we have the function to get the set of reachable states from a current state. So we have our state, and we first need to unhash it, convert it into the peg form. So what our peg form is, by the way, I didn't really explain this. It's just a vector of 12, 0, 3, and 4, just to make it easier to add and remove from the pegs. So we go through each peg, and we get the peg. If the peg is 0, we can't take anything off of it, so we just continue. Then we get the character that's at the top of our peg, which will be the rightmost character. And we then set the peg equal to everything except the last character. We just chop it off. So we're taking we're taking the top character of one of the pegs. If our peg becomes empty, we now represent it as a 0, because that's the standard that's in the question. We represent the peg that's empty as a 0. It's a bit annoying, but it has to be done. Then we go through the rest of the pegs, making sure we're not taking one off and putting it back on the same peg, because that's not allowed. I can show you why it's not allowed, because it says here, another peg. Okay, anyway. It wouldn't actually matter, believe it or not, which we'll come on to later. But yeah. So string temp. So what we do is we temporarily store the value of the peg that we're adding onto. So it could be 0, 1, 1, 2, whatever. So we temporarily store the value of the peg that we're adding onto, and then we add on the character onto that peg. So if it's 0, we're then replacing the 0 with whatever the number of our wall is. So we might replace 0 with 2 if we're adding a 2 on. If it's not 0, so if we already have stuff on the peg, then we're then adding on top. We now have our list of new pegs, which we can make a hash of, put it in our answer. And since we're using a set, there will be no duplicates, which will be useful. And we're then going to, after we make our hash, we're then going to reset our peg back to the temporary value that we had. Then once we've finished with taking the ball off of one peg and adding it onto the others, we're then going to put the ball back on top of the peg that we took it off of, and then we move on to the next peg and we repeat it again, and we keep doing it until we have all the set of states that we can reach from a current state. Once we have these three functions, now the main function is actually pretty easy. So we get our start and end, and these are hashes, these are strings. So what we can do is we can make a map of our distance. This distance shows what is the minimum number of moves needed to get to a state. We also have a queue, which is what we use for a BFS. I recommend, if you don't know what a BFS is, definitely looking that up. That will definitely be useful for any future buyers. But I can explain it very quickly. What we do is we visit nodes in the order that they are received. So if we visit a state after one move, we want to visit that peg. When we want to take the peg that we just visited and then look at all its neighbors, and in that way I'm trying to think of the word. we search for the next states from all the states of distance 1 before we move on to the states from distance 2. And that just ensures that the distance we get on my map is the minimum. It's just a simple way of doing it. But if you're a bit confused by that, I didn't explain it very well, you can just look up a bit more about BFS. And then we can add our start state into the queue and set the distance of the start state to 0, because obviously we get to the start state in 0 moves. And while the queue is not empty, we look at the front of the queue, we get all the states that we can reach from our current state, and we set the distance of the state to the current state plus 1 if it hasn't already been seen already, and we add that state into our queue to be looked at next. At the end, once our BFS/search is finished, we can then output the distance to the end hash. And if we run this function, let's test it. So let's test it with, let's do this one. So we're going from here to here, 7, good. Let's test it with 0. It's always very good idea. One tip, if you're writing a question like this, always check that it works for the case where there's 0 or there's 1, like the small ones, the boundary cases, just to make sure that the function is probably working for everything. Because if you get all these right and then you miss out 2 marks for getting that wrong, then that's not very good. And even if you're not sure your program is working 100% of the time, if you can get it working for 0 and 1, you can get 6 marks with an incomplete solution, which is pretty good. Anyway, let's check this last one, because it's the biggest one. And 9, perfect. Okay, so part A works. Now on to part B. What did I just do? So this is, I've just copied and pasted this from the other file because we're going to use it again. So this question says, how many game states have 9 moves available? So what we can do is, first we need to, so our 2 steps to solving this question are, first we need to get the list of all possible game states. Second, we need to go through all these game states and check, using our function that we made earlier, how many different moves are there available. And if there are 9, then increase the counter by 1 and then print out the counter at the end. So we can make a set of all our states, perform a search like earlier, but we just add every single state we visit, we add it into the set. So eventually, since we're starting from this position and we're just finding all the different states, we are going to exhaustively search the entire problem space, and we're going to find all the different possible states. It's a pretty neat way of doing it. Then we do the thing that I said, we just create an answer, we check if there are 9 moves available, increase counter by 1, and output the counter. Very, very easy. And, well, once you have part A, it's really easy. Part A is the hard bit, isn't it? 288, and it says 288, perfect. 3C. Okay, here we go. So the question is, suppose the starting configuration is 1, 2, 3, 4. How many different states can the game be in after 2 moves? How about 4 moves? So what we're going to do here is, again, we have our BFS search from before. That finds the minimum number of moves to get to each state. So all we need to do is count the number of states that can be reached after 2 or fewer moves and after 4 or fewer moves. The reason I say 4 or fewer is that we have this key insight that I need to explain here. If we can get somewhere in n moves, we can get there in n+1 moves. If we can get there in 3 moves, we can also get there in 4 moves. If we can get there in 2 moves, we can also get there in 3 moves, and so on, we can get there in 4 moves. So it's quite easy to prove this. All we do is we take the last move we're doing. So let's say we're moving a ball from the first peg to the second peg, and that's the last move that takes us to a state. But instead of doing that, why don't we just add an intermediate step for no reason? What if instead of going straight from 1 to 2, we go from 1 to 3 and then to 2. So now we've reached the exact same state, but we've used one extra move. And that's the entire proof. So all we do is we count how many states are reachable in less than or equal to 2 moves and less than or equal to 4 moves. So again, we do the exact same BFS as before with our distances. And we then just have our 2 answers. And we go through all the entries on our distance map, and we just check whether they're reachable in 2 or few moves. Increase that. 4 few moves, increase 4 by 1, and that's it. Very, very simple. This question is nice because part A was not too bad. Parts B and C were super easy. Once you go part A, parts B and C, you can just get them. So now, part D. This is, I'd say, the one I'm going to have to do the most explaining for. So, here's what the question says. Consider a variant of the game where there are 8 pegs, 8 identical balls, and each peg has a height between 1 and 8 inclusive. If there are 2023 different states of the game, what are the height of the pegs? So let's just take apart this question. 8 pegs, okay, there's 8 pegs, pretty simple. 8 identical balls. So identical meaning that the balls are no longer labelled 1, 2, 3, and 4. They're all labelled 1, or they're all labelled the same thing. Each peg has a height between 1 and 8 inclusive. That's what it means by height is that if your height is 3, you can only have 3 balls on it at a time because you can't have a 4th one, because if the height is 3, you can't stack 4 balls on it. So the height just shows what is the maximum number of balls we can have on a peg. Then we need to find out how many different states there are of the game. And so we need to find out, given a configuration of heights of pegs, how many different states are there of the game? This is quite a challenging question. And what we're going to do is we're going to propose a method to count the number of states reachable if we know the heights of each of the pegs. Then we can go through every single height of the peg, peg height configuration, and for each one check whether the number of states are 2023. If it is, then print it out, and that's it. And the reason this is doable is because each peg can only have a height from 1 to 8, and there are 8 pegs, the number of different ways of arranging the heights is around 17 million, which you can calculate by just doing 8 to the power of 8. And the actual number of configurations we're checking is a lot less, because we can actually remove a lot of duplicates. Because, okay, imagine you had 3 pegs. If you had 3 pegs of heights 1, 3, and 1, that's the same as if you had 1, 1, 3 or 3, 1, 1. So you can actually remove a lot of different combinations. So the way I'm iterating through the combinations is I am going through basically every binary number from 0 up to this crazy big number, and then taking each set of 3 bits and adding 1, and that's the height of the peg. So by doing that, because I'm going through every single binary number, we're going to get every single possible combination of bits. Alternatively, you could have 8 nested for loops, each representing the height of a peg. You can have I going from 1 to 8, J going from 2 to 8, K going from 3 to 8, so on, so on, so on. Or you can... Sorry, I actually said that wrong. I going from 1 to 8, to be, J going from 1 to 8, K going from 1 to 8, and so on. Alternatively, I mean, if that's easy for you to understand, you can also do that. For me, I find this quite easy to understand as well. All we do is we just we go through each of the 8 pegs, and we then get the bit at a certain position, and we then calculate the height. So let's explain how this works. So first we create a mask, and this mask is going to be the bit 1 shifted. So we're going to have the bit 1, so we're going to have 0, 0, 0, 1, and we're going to shift that number 1 along by a certain number. This is what this power2 function does. It just shifts the number 1 along by a certain number of bits. And so what I've done is that 3 times j plus 0, if I want, so since we're looking at bits in blocks of 3, we're going to, each block represents 3, so if we're on the j equals 1 block, we've already seen 3 bits, so we skip over 3, or if j equals 2, we've already seen 6 of the bits, so we skip over 6. That's what the 3 plus j bit is. Then we have plus 0, plus 1, plus 2. So that's showing the first bit in the triplet, the second bit in the triplet, and the third bit in the triplet. And we get the value of the bit by just checking whether it's 0. If it is 0, if the value of that bit is 0, then we're going to treat it as 0. If not, then we're going to treat it as 1. We can use the AND operator, and this will do a bitwise AND operation. So what this means is, if this number I, the binary representation of number I, and the binary representation of this number both have a 1 in that position, it will also have a 1 in the result of this operation. So we've created a mask here where all the bits are 0 except that 1 that we're trying to focus on. If the result of this bitwise AND is 0, that means that the bit there in the original number was not 0. If the result of our bitwise operation is not 0, that means the bit there was 1. That's what this bit function does. We can get the value of the 3 bits, and now we just treat these 3 bits as a normal binary number. So the first bit, we shift it to the left by 2. The second bit, we shift it to the left by 1. And the third bit, we shift it to the left by 0. So now we have this binary number like this. As I don't know which way the camera is, but 8, 4, and 1. Or it might be 8. Sorry, what am I saying? 4, 2, and 1, or 4, 2, and 1. One of those ways. We can then calculate the height by just adding these all onto 1. And because we're going through all the different bit combinations from 0 to 7 and adding 1, we would be going through all the heights from 1 to 8. So now we can just generate all the pegs of all possible heights. Next, this is not actually necessary for the correctness, but it will improve the speed by a large proportion. So what we do is, I'm only going to consider a set of pegs if they are ordered in non-decreasing order. So I'm only gonna, if I have, let's say, 1, 1, 3, that's good. If I have 1, 3, 1, that's bad. So by ensuring that our peg list is sorted, we're never counting the same arrangement of pegs twice. And the way I do that is I just check whether if the peg that we're currently at is less than the one before it, then it's bad, and we continue and we ignore it. Once we have our heights of the pegs, we can then use this function, which I'll explain soon, to calculate how many states are visible from that arrangement of pegs. If it is equal to 2023, we can then print out the sizes of the pegs, and that is the answer that we're looking for. Now we're onto the tricky bit, which is how do we count the number of states reachable from a certain peg configuration without actually performing the BFS, because that would take too long. How can we calculate it? So what I've done here is given given the height of the pegs, I need to find how many ways are there of arranging 8 balls on the pegs. And the way we do this is, first parameter is our actual pegs. So which pegs are we looking at? Second parameter is how many balls left do I have that I'm adding onto the pegs. K is which peg I'm currently looking at. So what we do is, we start off, we keep a total, which is going to total the number of states that we have. And we then consider a peg starting from index k onwards. So when we first call this function, remainder will be 8 and k will be 0. So we're starting from the leftmost peg and we have 8 balls to choose from. to add onto the pegs. If we have no balls remaining at any point in time, then there is one state reachable, which should hopefully be pretty obvious. And if the height of a peg is 0, we can just continue. Otherwise, we can add a ball onto the peg, which effectively reduces its height by 1. And then we can calculate the number of states with our pegs, with the remainder of our pegs, but this one is one shorter, and we can only consider the pegs from J onwards. The reason I only consider pegs from J onwards is that I don't I don't want to take off the reason I only consider pegs from J onwards is that I don't want to consider a peg that I've already added a ball to. So if I add a ball to the first peg, and then I move on to the third peg and I add a ball to that one, I don't then want to consider, oh, what if I go back and add a ball to that one? Because I would have already accounted for that at the start by adding a ball to the same peg multiple times. So by making sure I never choose a peg less than the one I'm currently on, we remove all duplicates. And this is a common tactic you'll see in a lot of questions. And so we can count the number of states using the updated pegs with the different height, and we have remainder minus 1 balls to choose from, to add on, sorry, and we start from J onwards. Then I can restore the height of the peg and move on to the next one, total up all the states and return total. And hopefully that makes sense. If not, if you have any questions, write a comment and I will answer, I promise. Because I understand that I might not explain everything perfectly. Hopefully you get a good idea. And let's run it and see what it does. This one will take quite a while to run. It will take about 10 seconds because we are going through 16 million iterations. It is going to take quite a bit. But it runs in under a minute, which is good enough for me. Gives us an answer. Here it is. 112.33388. Look at the answers. 112.33388. There we go. Perfect. And that brings us to the end of my Bio 2023 Round 1 questions walkthrough. I hope you enjoyed and I hope you learned something. And again, if you want to see the answers for Round 2 of this year or 2019, I'm not sure if it is 2019, I will leave my friend Erekle's channel in the description and his video, and he will be uploading the 2023 solutions soon, within a couple months or so. So stay tuned for that. If you have any questions, leave them in the comments. Apologies for my voice. Apologies if there are any issues. I think my camera might be slightly fuzzy. But apart from that, thank you for watching and I'll see you in the next video. Bye bye.